So, distinguishing among atoms, and we're going to start being able to tell atoms apart now, and what sets atoms apart, what sets elements apart. So, we have our atom so far. So, in other words, our atom so far is, our atom according to the Rutherford model, has a really small, dense, positively charged nucleus, and around the nucleus were J.J. Thomson's electrons. So we already knew about the electrons, and they're way out there. And the electrons are attracted to the nucleus because of the nucleus's positive charge. And because the nucleus has a positive charge to it, the protons in there, the blue protons that I've drawn, by the way, my protons are always going to be blue, my neutrons will always be red, and my electrons will be green. I'm going to try and continue that color scheme as far as I can. That with our positive charge here concentrated in the middle, our electrons are kept around the atom because of the electrostatic charge. Electrostatic forces, I should say, where a positive and a negative are attracted to each other, and positives are repellent, and a negative is repellent. So opposites attract, like charges repel, and because we have both of these forces at play here. We have all these neutrons here in the middle making the nucleus positive. We have the electrons that have a negative charge around it that are attracted to the nucleus, and that's what's keeping it around the nucleus. Okay, and then we also have the electrons that are repelling each other, and so they're not going to let each other get too close, okay, to the nucleus. Okay, and so they spread themselves out, and when they spread themselves out in 3 dimensions, when they're equally spread out, they create this spherical region within which the electrons spread themselves out. Okay, so that's how, it's kind of hard to draw a sphere in a 2-dimensional situation, particularly when you're just dealing with points of electrons. But we don't draw circles. Electrons are points. They are little particles. And so we can draw an implied line, okay, with individual dots of electrons, but we don't actually draw the circle when we're doing the model. But we've got 3 things in here that we need to define now. We have proton, is our blue proton. It has the symbol P+, or that's what we'll use in here. It has a mass. Okay, if you recall from Rutherford's theory that all of the mass of the atom is now centered in the middle of it. That's what made it so dense. That's what the alpha particle was hitting and bouncing off of which the alpha particle is bouncing. And so alpha particle comes in here and hits this dense center to the atom. So the things that are in the nucleus are the things that have mass. And the mass of a proton is 1 atomic mass unit, which actually is the simplest form of mass that we know how to measure. That's our basic, fundamental, underlying unit of mass. It has a charge, and this is also called an AMU. AMU. It has a charge of +1. The red things, also in the nucleus, are neutrons. Neutrons, I use the symbol N0, or sometimes you'll just see it as N. The 0 represents that it has no charge. It also has a mass equaling 1 atomic mass unit. Okay, it has a charge equal to 0. There is no charge on a neutron. The neutron's purpose, it serves as a spacer to keep protons from pushing each other apart. So if you look at our nucleus here, if we know that our electrons are spread out into this sphere because they're repelling each other, okay, and they've created this equilibrium between the attractive forces of the nucleus and the repelling forces of of the other electrons, why the heck aren't the protons in there pushing each other apart? All of our positive charge, all these protons with the positive charge are all concentrated in the nucleus. Okay. Well, we're going to define, there's something called a strong nuclear force. That's the actual name of it, is the strong nuclear force that holds the nucleus together. And it's when these particles are so close, okay, that they have the strong nuclear force, that they're able to stay together. However, that is acting against the repellent nature of the positive charges in there. And so the neutrons work in there as adding a little bit of extra space in between the protons to keep them a little further apart, because the further apart they are, the less force they're acting upon each other. Okay, so those are neutrons. And then finally we have electrons. Electrons, we have found, are very, very small. Okay, and the symbol we'll use is an E-. It has a mass that is equal to 1 over 1840, 1,840th of an AMU. But if you think about this, this is almost 2,000, and so the decimal of that would be 0.0005, which is 4 significant digits smaller than our 1 AMU. And so when we're finding the mass of an atom, combining the mass, unless we're trying to be hyper accurate, this is essentially equal to 0 AMU. And we don't usually count for the number of electrons in the mass of an atom. And electrons are allowed to move freely about the atom, and sometimes they leave the atom to join the electrons of another atom. Okay, this is the process by which we make ions. We'll talk about ions a little bit later. Okay, but electrons can leave. They're free to go. Those are the particles in our atom. We have protons, we have neutrons, we have an electron. Okay, protons have a +1 charge, neutrons have a 0 charge, and electrons have a -1 charge. So all of the mass, however, is concentrated in this speck in the middle of our atom, and that speck is called a nucleus. And this is a pet peeve of mine. Please pronounce the word nucleus correctly. This is how you say nucleus. Learn it, practice it, do not say it another way. Fortunately, it is also pronounced exactly the way it is spelled. Nu-cle-us. Not nucleus. No, there's only one U in there. It is nucleus. Nucleus. Words related to nucleus are nuclear. It is technically nuclear, but it's okay if you cheat and you say nuclear. Nuclear. It's okay to do that. The other one is plural for nucleus, which is actually an important thing for you guys. The plural for nucleus is nuclei. It's plural for nucleus. It is the traditional Latin spelling of the Latin plural of US is to end with an I, and so. The nucleus, it consists of protons and neutrons, and it holds almost all of the mass of the atom. Once we know the parts and we've identified the anatomy of the atom, we need to talk about how we talk about them. The example we're going to use, this is going to be called isotopic notation. There's 3 pieces of information. There's actually a whole lot more information here that we can glean from this notation, but there's 3 parts to it. The first one is this right here. This is the chemical symbol. These are this is the letter or the letters that you get from the periodic table that represent that particular element. So this one, for example, would be carbon. C is the chemical symbol for carbon. This guy down here, this is the atomic number. This truly is exactly what it sounds like. It's which atom is it? It's the number of the atom. This counts the number of protons. The atomic number is how many protons are in the nucleus of that particular atom. It defines which element the atom is. You count the number of protons. If there's 1 proton, it's hydrogen. 2 protons, it's helium. 3 protons, it's lithium. 4 is beryllium. 5 is boron. 6 is carbon. 7 is nitrogen, and so on. We have all of our protons. We have elements for counting 1 proton at a time. We have elements up through 118, and there's no in between. You can't have a 114.5 protons. There's no element that fits in between. So logically, there's only so many elements. And if you add a proton, guess what you're going to do? You make another element, and it becomes a different element. That's the definition of our element, is how many protons it has. So that is the atomic number. This is not to be confused with this dude up here, which is called the mass number. Now, if we go back and we look at our protons, neutrons, and electrons, 2 of our particles have mass, the protons and the neutrons. And so, if we're going to count our mass number is counting how many protons and neutrons. It counts our protons plus our neutrons. So, in this particular case, how many neutrons would we have in this particular atom? We would have 6. And how would we come to that? We get 6 neutrons because we have a mass number of 12, right? And 6 plus 6 equals 12, or this 12 minus that 6 equals the remaining neutrons that we need to account for our mass. Which brings us to the idea of an isotope. Okay, remember, blue is proton, red is neutron. Here, we have two nuclei. What is the isotopic notation for this nucleus? I'll give you a hint. It's that. This one would be 12, 6, carbon. Okay, how do we know that? There are, there's 4 protons, and there's 6 protons. We have the 6 blue ones, 6 protons. There's 6 protons, and so the 6 is our atomic number. There are a total of 12 things in the nucleus. That would be the mass number, 12. Because there are 6 protons, the chemical symbol is C for carbon, because this is atomic number 6. Okay, you will be handed you can look inside your books for your periodic table. You will also be handed a paper periodic table in due time. If this is 12,6 is our isotopic notation for this particular nucleus, what would it be for this one over here? Okay, we would have to change the mass number, right? And the new mass number would be 14. There's 8 neutrons there and 6 protons. These are both carbon atoms. They're both carbon atoms. They both have, or carbon nuclei, they both have 6 protons. But one has more mass than the other because it has more neutrons. These are called isotopes. They're atoms of the same element with different mass numbers. So both of these are carbon, but they have different isotopes. This is another name for this, by the way. We have a name for it, and I should probably give you the named notation. This is called carbon 12, and this one would be carbon 14. It is the ratio of carbon 14 to carbon 12 in the universe is fixed. Well, it's not fixed. It's known at any particular time. So imagine this. You die. Kind of a depressing thought, but when you die, you stop intaking carbon. We are not like plants. We don't breathe carbon. Okay? We eat carbon. Well, actually, if you die, it doesn't really matter. You stop taking carbon in. That establishes a moment in time when your body is not taking in any more carbon and you have stopped replenishing the balance between carbon 12 and carbon 14. Carbon 14 is radioactive. It decays at a given rate. It is you lose half of your carbon 14 every 5,730 years. So that ratio can be measured much later after you die. Say 20,000 years, 50,000 years after you die. Because the rate at which the carbon 14 turns into nitrogen is known and is consistent, we can determine the ratio between the two and figure out how long it has been since you died. This is called carbon dating. This is how we know fossils are old. This is how we know a lot of ancient texts are hoaxes, because the carbon dating. It doesn't go back as far, so they'll make paper in a very ancient way and draw stuff on it, and it'll be fake, because they'll be able to take the paper that it was printed on, and those plants were killed much later, okay, than when they're purporting the actual writing was done. And so it's how we determine the age of really old things, not epically old, not like millions and millions of years. We use other dating for that, but as far as biological samples or former biological samples, we use carbon dating to determine their ages, and it's very, very accurate. That's what we use for isotopes, and carbon 14 is one of them. This being said, carbon 14 is very rare. Carbon 12 is about 98%, and I'm just guessing here, but I'm using these numbers for illustration purposes. Carbon 12 is about 98% of all the carbon in the universe. The rest of the carbon is carbon 14. When we talk about the mass of carbon, you can't just look at a particular atom and determine how many neutrons are in it. And so what we need to find is an average value for all of the masses of all the carbon atoms. And because we can't sit there and pluck out each carbon atom, we can't, there's one and then there's one and then there's one. We can't pull them out individually and count them because there's too freaking many of them. They're small and they're all over the place. We have to use what's called a relative abundance. And the relative abundance it's the percentage of each isotope of an element present in nature. So in this particular case, the relative abundance of carbon is 98% carbon-12 and 2% carbon-14. I'm going to tell you again, my numbers are off. These are not the real numbers. I'm just making them up for argument's sake. We use this relative abundance to find the average atomic mass. And I need to move to a new page. Calculating the average atomic mass. Average atomic mass and just saying atomic mass means the same thing. Works like this. If you remember your numbers earlier from the notes, 98% was carbon-12, 2% was carbon-14. And this was the relative abundance of carbon. To find the atomic mass, or the average atomic mass, we use these percentages to weight our mass numbers. And so we will multiply 98% times 12. When we multiply by a percent, we must move the decimal twice. This becomes 0.98 times 12 AMU, which is the mass for carbon-12. We will add 0.02%, not percent, crap. 0.02 times 14 AMU, okay, and this is going to equal our atomic mass. Okay, so it's this percentage times that number plus this percentage times that number. Figure this out, 98% times 12 is going to be 11.88, I believe. 76? Oh, 24, not 12. Duh. Thank you. Plus 2% of 14 is going to be 0.28. So these will add to 12.04. That would be our average atomic mass. And if you look at the number, it should make some sense that if we're so heavy towards our carbon-12, that this number is going to be very close to carbon-12. And if we just have a little bit of 14, it's going to be a little bit higher than 12 rather than lower than 12. I'm going to give you another example because this isn't always just 2 isotopes. There are some elements out there that have 7 different isotopes. And so to find the average mass, you have to do this for all 7 of them. You're not going to have to do that, but I will give you one that's relatively simple. Hydrogen has 3 isotopes. 1,1 hydrogen, by the way, has how many neutrons? 1 minus 1 gives us 0 neutrons. This is called protium. 99.00% of all of our hydrogen. There's 2,1 hydrogen. This is called deuterium. Deuterium is 0.88% hydrogen. Again, I'm making these numbers up. Okay. And then 3,1 hydrogen is a third isotope that actually exists. These are the 3 isotopes of hydrogen. This is tritium. Okay, protium is proton, right? Protium is 1 proton. And then deuterium has 2, du means 2 mass things, and trit means 3 mass things. Okay, that's how they got their name. And this is the rest. So this would be 0.12%. So calculate the atomic mass. So we would do 99%, which would be 0.99 times 1 AMU plus. Now here's where students get tripped up. This is a very small number. Don't forget to move the decimals. Don't multiply by 0.88. 0.0088 times 2 AMU. And the last one, we have to do the same thing, 0.0012 times 3 AMU. Are we okay with how we're tracking from 0.12% to this fraction and 0.88% to this fraction? When you have your calculate the average atomic mass problem, you're going to have to move that decimal 2 places every single time. This is the most common mistake on this problem, is not moving your decimal correctly for the percentage. So stay on top of that. Don't let yourself do it. That's going to be 0.99 plus 0.0176 plus 0.0036. And if we add them all together, there's a couple zeros there. Forgot about the zeros for the sig figs. And so we get 2, carry the 1, 1, carry the 1, 1, carry the 1, 0, carry the 1, 1. So our average atomic mass would be, down there. Okay, 1.0112 atomic mass units would be the average atomic mass for this element. Is that clear? There is one last thing. We talk about the atomic number being the number of protons, the mass number being the protons and neutrons. Our electrons, because atoms are neutral, that means that the charge, if it's an atom, the charge is balanced. And so you can glean from this number right here, because we know that there are this many protons and that the atom is electrically neutral, from our number of protons, we can determine the number of electrons because they'll be equal to each other. I don't want you to think that the number of electrons will tell you the atomic number. It's just very often they're the same, and they equal each other when you have a neutral atom. But electrons can change atoms. Electrons are free to move. And so sometimes you'll have a particle that used to be an atom that has either gained electrons or lost electrons. The atomic number still stays with the number of protons. Okay, and that's it for today.